all the presenters, everyone that attends this conference is so friendly, so willing to teach, so willing to learn from you too. So it's not just watching these videos, it's kind of getting that insight afterwards and around at dinner, at drinks, like all the other aspects of the conference besides just like that technical information.
Okay, well, good afternoon, everybody. Welcome. Thanks for coming. As you can see, we're going to be talking about linear algebra in C++, and in particular the Eigen library, but we'll also get into a few other topics related to linear algebra. So just a little outline of how I thought we'd proceed first. I thought I'd, it'll help if I bring it up. I thought we'd go through like a short and high-level history of linear algebra in C++ going back to around 1998 and then up to the present day. We'll then shift focus to the Eigen library, which is the main point of this talk. And then we'll look at the new linear algebra interface coming in C++26. It'll just be high-level basics, but we'll also look at how it can work together with Eigen. Okay, so just a few disclaimers and caveats. This presentation is more on solving problems using the Eigen library and what's called the BLAS proposal in C++26. So I'm not affiliated with Eigen. I've used it in financial programming, that's my background, and in teaching. So I'm not an expert on the source code. I'm not an expert on expression templates. But I should also point out that, again, as I mentioned, my background's in finance. So there will be a couple of examples that come from that domain, but I think that they'll be they should be fairly straightforward and reasonably clear, so they could be applied to any other number of other domains. So my goal here is just to share some things that I know and some topics that I thought you might be interested in, and hopefully useful. Okay, you have to excuse me. I think being high and dry in Denver has kind of caught up with me. All right, so let's take a little trip back to 1998, and we will fly back with the queen of the skies at the time, the venerable 747-400. And around this time, the HAL 9000 computer was operational at the University of Illinois research facilities in Champaign-Urbana. Since then, though, they've came out with this miniature version that you can show you here.
I'm sorry, Dave. I'm afraid I can't do that.
Anyway, you probably had one of those big, heavy CRT monitors and probably running Windows 95. And we were just building up to the dot-com bubble, which 2 years later popped. So some of you might remember that. All right, so in 1998, around then, C++ is really growing in popularity, and especially in financial programming. It's really, really big. You know, all the financial software companies and financial institutions are eager to adopt C++. But for those of us who were in quantitative programming, so like option pricing models and risk management, that sort of thing, we found that there was no support for linear algebra. So kind of left us pining for Fortran. So your options at the time essentially were, you could write your own matrix class and operations, or you could try to convince your boss to buy a commercial library. So I thought I'd go through a few of the open source linear algebra libraries that started to appear in the early 2000s. What I'm going to go through here, though, it's not an exhaustive list. These are just libraries that I'm familiar with, a few I've worked with. But this is by no means an exhaustive list. There are a few more. But the first one that I worked with was the BLAS library in Boost. And BLAS stands for Basic Linear Algebra Subroutines, which have their origin in Fortran. This was released in November 2002. It had the BLAS functionality, and that meant matrix and vector representations, matrix addition and subtraction, matrix multiplication, and there were several types, so matrix by matrix multiplication, matrix by vector, vector dot products, and scalar multiplication. It also computed matrix and vector norms. So you were still on your own, though, for linear solvers and matrix decompositions. The authors themselves on the Boost website state that it offered good but not outstanding performance. So I did use it for a project. It wasn't bad. I just found it a little difficult to figure out how to use it. Also, as they have on the website, its last major improvement was in 2008. So if we move a little bit further in time with what we'll call next generation linear algebra libraries, and again, this is not an exhaustive list. Eigen came out in 2006, Armadillo in 2009, and then later was the BLAS library in 2012. These are all expression template-based libraries. Armadillo was not originally, but as I understand it, they've moved towards more of an expression template-based library. Sorry, excuse me. So they include the usual BLAS functionality that I mentioned previously, plus number of decompositions and solvers. So things that you might have found in the old LAPACK libraries in Fortran. I've not used BLAS, but I attended this talk in 2016, CppCon, when we were back in Bellevue. It was a bit more convenient for me, but could just roll out of bed and get my car and drive over. Anyway, it was a really good talk, and if you want to learn more about it, highly recommend checking it out. But interestingly, he did performance tests against a number of different libraries. I can't remember, something like 8 to 10 different libraries. And interestingly, one of them was Eigen, and interestingly, it placed actually quite high. It was above most of the competition. Okay, so now bringing us back to the present day, I'm going to mention MD-span. This is how they describe it in the proposal, but essentially it can impose a non-owning multidimensional array on a one-dimensional contiguous memory container, excuse me. Dang it. I'm afraid this is going to happen. Sorry. So, for example, you could have a vector, a stood vector, and you could impose then a two-dimensional structure on a one-dimensional vector. And that can represent a matrix. You could also use an eigenvector XD type, which we'll talk about shortly. That's also in contiguous memory. And then there's MD array, which is the owning analog of MD span, and that's due out in C++26. It's proposal 1684. But the reason I mention this is the new linear algebra features that they've been accepted for C++26, they use MD span to represent matrices and vectors. And what it is, it's a free function linear algebra interface based on the BLAS. So what that means is you can use an arbitrary BLAS library, but the interface will always be the same, and it'll be standard, which is a nice thing. So if, no matter what library you're using, your code remains standard. And as I said, a matrix is represented by a two-dimensional MD span, and a vector is represented by a one-dimensional MD span. Also, as I understand it, with the major compilers and library vendors, they will include a default BLAS. There's also a reference implementation on GitHub that I'll talk about in a little while. Okay, so moving ahead to the Eigen library, which is kind of the main focus of this talk. The owl you see there, it's their mascot. It's on their website. So as they describe it, a C++ template library for linear algebra offers these things, matrices, vectors, and so forth. Within the scope of, thank you. Within the scope of numerical solvers exists the matrix decompositions, and some of which we'll be talking about here shortly. I heard a sympathetic sniff there. I appreciate the gesture. Okay, so version 1 was released in December of 2006. The latest release came out about 3 years ago. It's currently released under the Mozilla public license, but originally when it was first released, it was the very restrictive GPL. And then they moved to the LGPL. And then I think it was around version 3.1.1 that they adopted the Mozilla license, which of course is a lot more advantageous for us because it's a much more liberal license. It's header only, so it's very easy to include in a project. And it relies heavily on expression templates and lazy evaluation. It's popular within a number of domains, among which are finance. Again, that's where I come from. But Armadillo is also very popular in finance. You can also find it in medical and pharmaceutical research. One example is in the Stan math library. This is used a lot in pharmaceutical research and with pharmaceutical simulations. It's a, as they call it, a differentiable they call it differentiable C++ for linear algebra and probability. It contains a lot of Bayesian statistics. It also has differentiability in it, which is very fast. It's also used in cancer modeling. And if you were here 2 days ago and attended Ribo Zhang's talk, you would have learned a bit more about it. If you weren't able to see it, I highly recommend it. One reason, first of all, it's very interesting to see applications in cancer research. It's really cool. The other thing, though, is that he used other features in Eigen that I'm not going to cover here. So his talk was, in a sense, orthogonal to mine. So if you want to get even a wider view of Eigen, check out his talk. Again, if you haven't seen it already, it'll be out on our YouTube channel soon. You can also find it in data science and machine learning. This can be seen, one example is it was adopted for the TensorFlow library. And also you might find it in experimental physics. An example of this is it was adopted for what's called the ATLAS experiment tracking software, which is used at the CERN Large Hadron Collider in Switzerland. Okay, so Eigen offers both dense and sparse matrix representations. We will concentrate here on dense operations, and the core class for that is, surprise, surprise, the matrix class. It's part of a class template hierarchy, which you can see here. But one thing to note is that most of the member functions are defined on the matrix base class. Sorry. Give me a second here. I don't know if this is going to help or not. Can't believe this is happening. Okay, so the eigenvector class, there's also an eigenvector class, which is an m by 1 column vector. Let's see, where is I going with this? I was a little bit lost. Which we will also be using in this presentation. The eigenmatrix class supports the usual numerical types, so int, float, double, and complex with double real and imaginary parts. There are various aliases of the matrix class. First of all, there are aliases for fixed square matrices up to 4 by 4. So for example, a matrix 4i represents a 4 by 4 matrix of integers, and a matrix 3f is a 3 by 3 fixed 3 by 3 matrix of float types. Now it's a nice thing that they give you these aliases, because if you had to write all these things out, you'd have to write out really with templates, and a lot of template arguments is going to get really messy in a hurry. Now, for most of us, though, these fixed dimension matrices aren't going to help us a whole lot, right? Because most of the time we're not going to know how many rows or columns we're going to have in our matrix. So Eigen also provides an alias for dynamic dimensions, and in particular, a matrix XD, which is a dynamic m by n matrix of double types. There's also a vector XD alias, so same thing but for an m by 1 column vector. There's also a row vector, so 1 by m. And there's also a matrix XCD, and this is an m by n matrix of complex types. So for our examples, we're going to be focused on these two. Okay, so we'll look at a few ways to instantiate an eigenmatrix. So I'll just bring the matrix XD into the global namespace for convenience. One way is to use an initializer list of initializer lists. So it's kind of like a coffee table book about coffee tables. Each initializer list represents a row in the matrix. However, there's certain cases where you need to be careful here, because although data is taken in row major order, it's actually stored in column major order. And we'll see an example at the end where this comes into play. Okay, so you can also create a matrix just 4 by 3 and then populate it. It has overloaded stream operator, and you can also just assign them element by element, as you see here. Eigen, there are tutorials available. This is one of them. The documentation is quite good. There are a lot of tutorials, and so it'll help you get up and running pretty quickly. Okay, so the star operator implements the matrix product. This is not element by element multiplication. If you need element by element multiplication, Eigen also has array types, and the default multiplication operator there is element by element. And again, in Rebo's talk, that's the type of object that he was using. But for us, we're going to concentrate on the matrix type. So if you have a matrix A 5 by 3 and a matrix B 3 by 5, multiplication's defined, you just say A star B and you're done. Also, Eigen provides an overload of the stream operator so that you can see out your results to the screen. And then all afternoon I was fine, and then of course when I came down here it started again. Okay, scalar multiplication is also defined, so if you want to take half of each element in A, just 0.5 times A, and you could store the result in a new matrix instance. And when you do that, there's your result as expected. It also works with multiplication assignment, so you could, say, take twice each element in the matrix B and then assign it back to the same matrix. This also applies to eigenvector types, such as vector XD. And matrix addition and subtraction are similarly defined with the plus and minus operators. So for example, we have our matrix A and suppose another 5 by 3 matrix C, and we add them, and shazam, you get the result. But again, it's very nice because it flows mathematically, as you'll see on the next slide. It's also, here's an example with subtraction. I just put the vector contents in the comments, just U minus V, and you get your result. Okay, as I said, it's very nice because you can take mathematical statements and pretty much as they're written mathematically, write them into code. So for example, if we have these two mathematical expressions, then we can map them into C++ using Eigen, as you see here. The only difference is this using the dot member function here. And the reason is that a vector XD is a column vector, so if we tried to multiply U times V, it would be undefined. You could use, you might recall there was a row vector type, but if you do that and if you get the order mixed up, you might end up with a singular matrix. So it's safer and best just to use the dot member function. Now, one really cool thing about Eigen is you can iterate through an eigenvector container and apply STL algorithms. This is a really, really nice feature. So as an example, let's populate a vector XD with random numbers taken from a t distribution. And we'll use the new random number generation. Well, it's not all that new now, but that came out in C++11, and apply the std generate algorithm. And then we can apply the max element algorithm to find the maximum random value in the result. Okay, so we define a vector XD called U with 12 elements. And we'll use the Mersenne-Twister random engine, the student t distribution class, and so for a t distribution with 5 degrees of freedom. And then we'll apply the generate algorithm just like you would do with a standard container. So there's no difference. So begin and end are defined. You can also use std begin and std end if you wish. And then when we're done, we can locate the maximum element by applying the algorithm that you see here. Maybe I'll just do this. Also, eigenvectors can be used together with STL containers in standard algorithms. So as an example, suppose we want to take the dot product between a vector XD and a std vector. So let's create a std vector of the same size. Note that the vector type in Eigen also has a size member function. So again, it's very similar to what you find with standard containers. And then we'll generate 12 more random variates from our t distribution. And then we can calculate the inner product or dot product using the inner product algorithm. And again, it's just like, you know, these were, just like it would be an STL container. So again, there's some really, really nice features about Eigen. There's also a unary expression that's similar to transpose that's provided with Eigen. So for example, and you can apply this to an entire matrix or a vector. So if you have, say, a matrix vals, like you see here, you can call this member function called unary expression, and you just pop in an auxiliary function, just like you would do with std transform. And this could be a lambda, it could be a functor from a class, it could be a standalone function. Again, just like you would use with standard algorithms. And taking the square of each, you get the expected result. Eigen decompositions. There's, I can't remember, about maybe 15 or so. And a complete list can be found in the documentation. We'll look at a couple of examples. First, we'll look at the QR decomposition. This is the householder QR class in Eigen, named after the famous American mathematician. So what this says is for an n by p matrix A, and we'll take the case where the number of rows is greater than or equal to the number of columns, and the rank of the matrix is p. That means that all p, excuse me, columns are linearly independent. And what this says is, excuse me. CppCon 2024, something to remember. Anyway, so what this says, under these conditions, that means we can express the matrix A as the product of an n by p matrix Q, which is orthogonal, and a square matrix R. I'm sorry, so it's the product of those two matrices Q and R. as Q is orthogonal, that means if we multiply it by its transpose, we get the identity matrix. And also R is upper triangular, which is convenient for numerical routines. Next up is the Cholesky decomposition, which is represented by the LLT class in Eigen. Now you might notice it's a little aside, I pronounced it Cholesky. So for many years, this decomposition is used a lot in finance. So I heard Cholesky, Kolesky. But after researching it, I found that actually Cholesky was a French mathematician and also military officer who served in World War I and unfortunately was killed in action. But anyway, CHO in French is pronounced Cholesky, or is pronounced Cho, so it should be Cholesky. Little trivial factoid for you. So I'm going to run with it unless there are any objections. Okay. So what this says is if A is positive definite, then the square matrix A can be represented by the product of a lower triangular matrix L and its transpose, the product thereof. There are also a couple of others I'll mention here. There's also the LU, the lower upper decomposition, which is represented in the partial pivot LU class in Eigen. And it also offers singular value decomposition. There are two versions of this. The first one, Jacobi SVD, is optimized for smaller matrices. And for larger matrices, it's the BDC SVD, which stands for bidiagonal divide and conquer. So, there are these, but there are many more. So let's look at an example. So you're managing a fund, so you have a portfolio, and you represent the returns of that portfolio by the variable y. And we also have 3 index returns which we'll use to predict fund performance. Actually, this is a very common exercise in finance where you have a portfolio and you want to actually measure the sensitivities to movements in published indices like S&P 500, NASDAQ. Oh man, sorry.
Take a break maybe? If everyone is okay.
It's like everything is going wrong that could. Okay, so it's a common problem in.
Should we do a short break?
What's that?
Should we do a short break?
Well, we'll blow the time. Can we, or should I just keep going? Then let's just keep going, and maybe I can re-record it, or you can take me off the camera. Now, I apologize. I thought I was okay this afternoon. It was perfectly fine, and then all of a sudden, of course, when I come down here, it all starts. So there's a common exercise in finance where you have a portfolio and you want to look at the sensitivity of the portfolio to, like I say, these published indices. So we'll say we have n months of data or observations. And the way we do this is we're going to run a regression, thank you very much, where we seek the least squares estimates, beta 0 hat through beta 3 hat, that gives us our linear regression equation. So we're going to assume that the number of observations n is reasonably greater than p, and in this case, p is equal to 3. And we'll also assume that our index returns, the predictor variables, are not highly correlated. So in other words, the columns are taken to be linearly independent. So under these conditions, we can apply the the householder QR decomposition in Eigen. So as an example, suppose we have data over 30 months and we'll define a vector y mathematically containing the monthly target fund returns. And the matrix X will hold the monthly returns for each index in a separate column, plus there will be a column of ones for the intercept. In matrix form, this can be written as y hat equals x times beta hat, where this vector y hat, the design matrix X, and vector beta hat. So if we apply the substitution, we substitute x with QR, what you get on the right-hand side of the arrow then is Q transpose times y equals R times beta hat. And that's, we get rid of the R on the right-hand side because we pre-multiply by Q transpose, and because it's orthogonal, we get the identity matrix. And because R is upper triangular, we get a triangular system, which is easier to solve numerically. So again, our problem is to seek the best fit estimates for our regression equation. We have 3 predictor funds and intercept terms, so we create a matrix X, 30 by 4. But now we're going to populate it a little bit differently. You can actually assign individual columns to vectors in Eigen. And so for our column of ones, there's a function that just returns the number of ones that you put in the argument. So this gives us a vector of 30 ones, and this will go in our first column. Then the remaining data can also be assigned using individual vectors. Of course, in reality, we wouldn't be hard coding the data. It would be coming in from a database or something. So we could get the data, say, from a database, bring them into eigenvectors, and then assign them to columns in the matrix. For the vector y, the response vector, we'll just go back to the old way and use the stream operator. Okay. If you look at the X matrix, it looks like that. So you see the ones down the first column. Okay, at this point, 98% of the work is done. All we need to do now is apply the householder QR decomposition in Eigen. And it's just a case of calling the householder QR member function, which returns an object of the same name. It has a member function called solve. It takes in the y vector as an argument, and the results you get are your beta coefficients. And you're done. Really, really easy, really, really straightforward. If you write this out mathematically, then that's what you get, of course, rounding a little bit. Just one thing to note, you might notice that the intercept term is very close to 0, and in these types of problems, the intercept term is often omitted, but I just kept it in here so you could see how to do it. Okay, so this brings us back to the future, and so we'd probably be flying in something like an Airbus 350. And on your nice, sleek, large, flat screen monitor, you'd see some cool applications like Compiler Explorer, and ChatGPT. So we'll talk a little bit about BLAS. This is, again, proposal 1673. This is how they describe it in the documentation. So again, keep in mind, this is an interface based on an arbitrary BLAS library. It's scoped under std lineage in that namespace in the code. So sometimes it's actually referred to as std lineage rather than std BLAS. Just looking at some examples here in the left-hand column, These are the old Fortran functions, just a selection of them, not all of them. And in the middle column, these are the BLAS functions that are their equivalents. So the first one, scale, is scalar multiplication. Come down here, dot product of two vectors. The Euclidean norm. I apologize for the shading. It was an accident. I didn't have time to take it out. But there's matrix vector product. And this is the general form. But what we'll be looking at is just this multiplication here, just like a matrix A times X, which we'll get to here in just a second. And so on. So again, going back to portfolio management, you are often dealing with the covariance matrix of the asset returns in a portfolio. And there are two common tasks that you need to carry out. One is, I'm sorry, let me back up. You're also given a vector of portfolio weights, omega. What this means is it's the percentage that you have invested in each asset. That's what that represents. So common problems in quant finance are first to calculate the portfolio variance. Now you take the square root of that, you get the standard deviation, which is called volatility in finance. That's just the quadratic form that you see here. And for that, we have what we need in BLAS. But another common problem is to calculate the Cholesky decomposition. Again, this is very common in risk management. It's also used a lot in basket options pricing, where you're running Monte Carlo simulations. So again, the portfolio variance we can do in BLAS. We have to go elsewhere for the matrix decomposition, but we have Eigen, so we can use it. And then we'll see how we can go from one space to the other, so to speak, via it's kind of like an interface in Eigen. Okay, so to compute the quadratic form, we'll compute the right-hand side first, the sigma omega, and we have matrix vector product in BLAS. The way that there's a reference implementation available right now. It's on GitHub. I'll give you the URL at the end. But they have everything scoped under stud experimental, and then they use this namespace alias. So I'll just do the same thing. So it'll be studx dot : linalg. Okay, so we'll have a portfolio of 4 assets. We need to put the data somewhere in contiguous storage because we're going to need to use MD span. So we'll just put it into a stud vector. So I wrote it here in 4x4 form, so you can see that it's a symmetric matrix. Then we'll also store the weights in our vector omega. What this means is 25% goes in the first asset, we go 25% short in the second asset, and then 50% in each of the third and fourth assets. To kind of make it look general, we'll define a long variable n. The reason it's long is that's what Eigen expects. And also, when computing matrix vector product, we'll need a place to store the result. The result will be a matrix. So, and then we'll need an MD span that refers to that. But we need to create the vector, so we'll just create it now. So the next thing is you need to make MD spans of all these things. So as you can see in the first argument, this is just the location of the data that's in each of those vectors. For the matrix, you give it this extents argument, and what it says is there are two extents, one representing rows, the other representing columns. Each has a size of n. And similarly for the vectors, these each have one extent and also are of size n. Then we can apply the matrix vector product function. So the first argument is the covariance matrix represented by its MD span. Similarly for the weights and the what I call inner matrix vec, that's the temporary storage for the right-hand side multiplication. What we're left with now are two vectors, so we can apply the dot function in StudBLAS, and so you just put in the weights again and the result from the right-hand side multiplication. And you get a result of about 0.02. That comes out to about 0.07 annualized. And then to get the volatility, you take the standard deviation of it. Then the second task is to find the Cholesky decomposition of the covariance matrix. Again, we're assuming it's symmetric and positive definite. So therefore, a Cholesky decomposition exists. And that means there's a lower triangular matrix L such that sigma can be represented by the product of L and its transpose. What this gives us mnemonically is the square root of the covariance matrix. And you sometimes would actually see this sigma to the 1/2, okay? It's not a real thing, it's mnemonic. But what it is the multivariate analog of a standard deviation. So there are no decompositions in StudBLAS, so we'll use Eigen. Now, the key to this, going from one space to the other, is this object called an eigenmap, which is a view. And we can take a view of the matrix data that we have that is referred to by our covariance matrix MD span. So essentially what you get here is a view of a view. And it can be used in place of a full matrix object in Eigen. So this is very convenient. So this is the gateway between Eigen or between StudBLAS and Eigen and back. Okay, so we create an eigenmap. We give it the address of the covariance matrix MD span, and it has n rows and n columns. Now again, about 98% of the work is done here. All we need to do now is create an LLT object, and we'll call it Cholesky, and it takes in the Eigen covariance matrix map. You could also put in a full matrix object for the constructor. So both will work. And then once you're done with that, you can get the L matrix by calling the matrix L member function. So this is a lower triangular matrix. And then its transpose is upper triangular. But if we, now let's go back and we're going to store the result in StudBLAS. So you might be working in StudBLAS, you don't have decompositions. So you go to Eigen, you get the result, and then you want to bring it back into an MD span. So you do this in the usual way. You give it the location of the matrix data, and you give it two extents, again, each of size n. But then you look at the results, and oops, it's in upper triangular form. The reason for this is MD span, the default is row major order. And remember at the outset is that an Eigen matrix stores its data in column major order. So what you need to do is create a mapping in for an MD span, and in particular what's called a layout left, and this will give you column major order. So what you do is you give it the extents again in the constructor argument. So again, 2 extents, each of size n. And then when we create the MD span, we use a different constructor, which now takes in the location of the data again, but instead of the extents, it brings in the mapping, which you see here. So that's the location of the data, and that's the mapping. And when you look at your result, now we get what we expected. Okay, so brings us to the end. Just to summarize what we've done. So we found that linear algebra options originally were very limited for C++98, but as we got into around the mid to late 2000s, we started to see some robust open source linear algebra libraries for C++, and among them were Eigen, Armadillo, and BLAS. And Eigen is a header-only library which relies heavily on expression templates. It provides basic linear algebra, like you'd find in BLAS, plus linear solvers and matrix decompositions. And a very cool thing about it is it's STL compliant, so you can use eigenvectors with STL algorithms. And then there's this unary expression function, which acts like stood transform, and which can be applied to a eigenmatrix or vector. We also looked at the BLAS interface proposal, 1673. And again, this is accepted for C++26, so another year and a half? And this provides matrices and vectors, addition, subtraction, multiplication, norms, and so forth. But if you do need decompositions, then you can go via an eigenmap to get into the eigenworld, get your result, and then you can bring it back into stood BLAS space. Okay, just some references here and some people I'd like to thank. First of all, the Eigen documentation can be found on this URL. As I said, the documentation is quite good. And lots of tutorials, so again, you can get up and running fairly quickly. The stood BLAS P1673 proposal is available at the usual place, and the reference implementation can be found on this GitHub site. I'd like to thank Mark Homan, who helped me out a lot with the content for the stood BLAS part of the presentation. Also, if you want to find out more about it, I highly recommend you go back to CppCon last year and watch his video. He gave a presentation on the topic, and it gets into a lot more detail than I did. And the slides are also available on the CppCon GitHub site. For the least squares solution for the regression problem using the QR factorization, if you want more information, this is in the classic text by Golub and Van Loan called Matrix Computations, section 533. I will have sample code available for this presentation. I haven't put it out there yet, but I will. I also provide some additional examples like singular value decomposition and some other things. So it's this plus a little more. Also, I should add that getting started with Eigen is very easy. All you need, again, it's header only. You just need to include it in your project. But BLAS is a little trickier. Eventually, I'll try to write up a summary of how to do it, at least in Visual Studio. But that might take a little more work. Finally, this is kind of a shameless plug, I guess, but technically I used Chapter 8 from a book I wrote as a reference for this talk. So it will be out, they're saying like early November, so we're almost done with it. But I'm not asking you to buy it. If you can't afford it, just borrow it from some rich dude. If you'd like to contact me, this is my email address. I am also the student program chair here at CppCon. And if you'd like to connect on LinkedIn, this is my address. So, thank you very much, and thanks for putting up with me. And yeah, I can try to take a few questions here.
Thanks for the talk. You mentioned the point of lazy evaluation in Eigen, I think, or maybe Armadillo. I was wondering if, since compilers have improved a lot for optimizations, if that feature of those libraries that are targeted at doing lazy evaluations for performance purposes are still relevant and still compete with just straightforward code and letting the compiler optimize stuff?
That's a good question. I actually tried something out. It was just it was for my book, a simple example on expression templates. And when I ran it on my old Mac computer, which has, I think, 2 physical cores, you could see the difference. I mean, it was quite dramatic. Then I ran it on this computer, which has 8 physical cores, and I bought it a couple years ago. And actually, between expression templates and the non-expression template version, there wasn't much of a difference. So I'm not sure how it would be now. But that's a really good question. Maybe, I know, my spare time, I'll test it out.
Hey,
Yeah.
thank you for the talk. I have a question in particular about the column measure and like a row measure. Do you know why one library chose one and then the chose the other?
I wouldn't know. You'd have to ask them.
Okay. All right, thank you.
Sure.
To quickly answer the last question, column major order is actually faster for doing matrix operations. Now, the question I had was, because it's actually column major order, do you know if Eigen plays well with Fortran, which always represents matrix and column major order?
Not sure. It's a C++ library, so I'm not sure how that would work.
All right.
It's kind of above my pay grade.
Okay. And another second question. Do you know if the Eigen library is faster than standard Fortran implementations of the same?
No,
no. Okay.
I wouldn't know. Again, that's maybe another fun project to do over this, like over Christmas break or something. I don't know.
All right. Thank you.
Sure.
Hi. If
Hi.
memory serves, these matrix operations, like the QR decomposition themselves, depend on a lot of BLAS type routines. I'm wondering, so will those within the library, I presume they're in the library now, will they be replaced with the stud-linelg ones when they're available?
You mean in Eigen?
Yeah, Eigen must come with its own set of those, right?
Yeah, it does. No, I don't think they have any plans to. I did send a question about a year ago whether they were working on an interface so that you could use it for the BLAS parts, and they said at that point, no. So
Okay,
that's the information I have.
Hi.
Hi.
Thank you for your talk. So would you see in an existing code base any real benefit from transitioning from interfacing directly with Intel MKL to using Eigen?
It could be. You can interface with the MKL MKL library. The standard the standard version is just all header only, but yet you can use external libraries with it.
With Eigen.
Yes. Yeah.
All right. Nice. Thanks.
Okay. Well, again, thank you very much. Thank you for putting up with me. I apologize for all this.